Hello all and welcome to Physics with Pranav. If you're new to my channel, I'm Pranav. I used to be a CAIE science and math student. I've tutored GCSE and A-level students from around the world in physics and mathematics, and I am an IGCSE world topper in science from back in 2013. In my videos, I provide you with a simple three-step approach that has helped me and my students achieve excellent grades in our exams. The approach is quite straightforward. I start off first by looking at recent past papers to identify the key concepts that are tested from each chapter. Once I've done this, I will then dive deeper into these concepts so you have a solid foundation and understanding of these concepts. And then finally, I will show how these concepts are applied to past paper questions so that you feel confident applying them yourself when your exam comes around. The videos that I make are based around the CAIE curriculum. So this video will focus on chapter 8, which concerns work done and power. However, if you are from a different curriculum, I still believe you can get a lot of value from my videos because a lot of the concepts tested at the GCSE level overlap between the different curricula. I also strongly believe that the methodology I use to solve past papers, as I will in this video, will prove helpful irrespective of what curriculum you study in right now. I want to mention that this video will focus on applying the concepts of power and work done to paper 2, the multiple choice paper. I made 4 other videos, or rather 3 other videos, which forms a part of a 4-part series for this chapter. 2 other videos explore the key concepts tested, dive deeper into them, and make sure that you know what you need for the exams. The other 2 videos, of which this is one, will focus on how to apply these concepts to past paper questions. So you can find the links for these videos in my description below. I also want to mention that in the links below, you will be able to find access to the playlist that I've created, where I have applied concepts from different chapters to past paper questions, as well as looked deeper into these concepts to try and understand them better and solidify the foundations. I want to mention that this particular topic has a lot of questions featuring in paper 2. So if anything at all, pay more attention to this video because you will find at least 1 or 2 questions in your multiple choice papers from this chapter. I also want to mention that there is a lot of overlap with this chapter and the chapters on energy, which is chapter 6 and 7. So that is also something to keep in mind. So if you want to appreciate those concepts better, feel free to check them out in my channel. So without further ado, let's take a look at how to apply work done and power concepts to paper 2 or the multiple choice papers. So the first paper we'll be looking at today is October-November 2023. So if I go down to find the question on work done and power, or it could also be energy. So there's a first question. A boy uses a rope to pull an object of mass m up a slope. The rope is parallel to the slope. The tension in the rope is constant and of value F, okay? So that's the force, essentially. The object moves a distance d along the slope and rises through a height h. How much work is done by the boy? So you'll find a lot of these questions where they give you essentially 2 distances, right? So you've got distance d, and then you've got a height h. And really, which value of distance you use in your formula for work depends on which direction is along the direction of the force, because the formula for work is force multiplied by distance moved in the direction of the force. So essentially, if we look at F into D, D is the distance along the slope, the force acts along the slope. So essentially, that distance D is in the direction of the force, therefore that answer is correct. But just to check the other ones, B is given to confuse you. It shows that it's force multiplied by the height. But obviously we know the boy is not lifting the object up. Instead, he is pulling it up a slope. So it can't be B. Now, if you look at C, C is, we don't even know what quantity that is because mgh is essentially the quantity for energy. And that's energy multiplied by distance. So there is no such quantity that exists. And then we have mgh square, which is essentially mgh multiplied by, well, h instead of d. So again, C and D are definitely wrong. B is there to trick you, so A is the correct answer. It's always good to cross-check, just to make sure that one of the other options is correct, but usually just one option is right. A microwave oven is rated at 900 watts. Which symbol correctly describes the meaning of this value? So the first says 900 joules are transferred every second. So a watt is essentially a unit of power, and power is work done per unit time. So it should be essentially work done, which is measured in the same units as energy, which is joules, and then per unit of time, which will be per second or minute or hour. But obviously, because we have watts, it'll be per second. So that is the right answer. Again, A is the right answer. And the other ones we can clearly tell are wrong because you've got amperes, transfer per second, volts, ohms. All of those are quantities that we'll learn when we look at the concepts of electricity, but none of those concepts. And again, there is electrical energy and there is electrical power, but none of those things give us electrical energy or electrical power. So this is the only one that essentially gives us the transfer of some form of energy per unit of time. So that is the right answer there. So moving on to the next paper. So the next paper is October number 2023. We're looking at variant 2.2. So if I go down, try to find the questions on work done and power. So we've seen some of these questions around energy. So question 10. An electric car is charged overnight. In 8 hours, 180 megajoules of energy is transferred. What is the power of the charger? So power is essentially work done over a unit of time, or energy transferred over a unit of time. Now we know that the energy transferred is 180 megajoules, or 180 into 10 to the power 6 joules, which is what I've expressed here in just zeros. And we know that this work is done in a period of 8 hours. So 8 hours is essentially, you have to convert that into seconds. So that'd be 8 multiplied by 60, because there's 60 minutes in an hour, multiplied by 60, because there's 60 seconds in a minute. And this gives you a value of 6,250 watts. We could see that our final answers are in kilowatts or megawatts. We know that to go from watts to kilowatts, essentially kilo means 1,000. So to go from watts to kilowatts, we have to divide that by 1,000. So that would have a value of 6.25 kilowatts, or around 6.3 kilowatts. So that is our right answer, A. So if I go down, can't see any more questions. So let's move on to the next paper. Now here we have October, November 2021, variant 2.2. So question 9. A box of mass m slides down a slope of length L against a frictional force F. It descends a vertical height D. So we have the system here. So you've got a mass m. It moves down the slope and it moves a distance of L. It also descends a distance of D. And we know that there's a force of friction that's acting upwards. As the box slides down the slope, it loses gravitational potential energy, and its work and it does work against the friction. So essentially, the gravitational potential energy that it has stored at this height D is lost as it falls down the slope, and it also does some work against friction. So which row gives the loss in gravitational potential energy and the work done against friction? So we know that gravitational potential energy is mass multiplied by the gravitational field strength multiplied by the height, or the height lost in this case. And we know the height lost is d, so it has to be mgd, right? Which means C and D are already wrong. It leaves us with options A and B. And then if we look at options A and B, the work done against friction, so friction acts along the slope, and it acts for a distance L. So work done in the direction of the force is F multiplied by L, not F multiplied by D, because the object is not falling like that. So essentially the work done against friction will be FL. So B is wrong, A is the right answer. Excuse me, still got a bit of a cold. So question 10 as well is a question around power. So rope connected to a pulley system and motor is used to lift different objects through different distances. The time taken to lift each object is the same, okay? So essentially the denominator in your calculation of power would be the same for all of these. What changes is the numerator, which is the amount of energy transferred or work done. The diagrams are not to scale. Which motor requires the greatest power? So essentially, the question here, if you want to rephrase it, is how much gravitational potential energy is gained by each of these different weights for the different distances that they move. Because they're doing it over the same period of time, which means, again, the denominator of the power equation will be the same. So if I look in this case, and I assume that the gravitational field strength or gravitational acceleration is 10, then you got a 10 kg mass multiplied by 10, moving a distance of 2 meters, which means you're going to have 20, 20 times 10, essentially giving you 200 joules of energy. It's gained. So motor has to, essentially transfer those 200 joules in a period of time, which is the same in all scenarios. In the second case, you have a 5 kilogram mass moving 3 meters, so it moves a greater distance, but it's got half essentially the weight. And because the gravitational field strength remains the same, we could see that a quick way of doing this, obviously you can multiply it out. You could say it's 5 times 3 times 10, which essentially gives you a value of 150, so 200 is still greater. But one of the things that I would quickly do as well is that is half the mass, and it's only 1.5 times the distance. So, that value will be lower than that value there. Yep. So if you look at the next scenario, we have a 10 kg object moving 1 meter. So that's already less than that, although the weights are the same, or rather the masses are the same, and the weights will be the same as well. It's moving a lower distance, which means it needs less gravitational potential energy being transferred to it. So that obviously cannot be right. And the last case, you have an even lower weight than 5 kilograms moving 3 meters. So if 5 kilograms moving 3 meters was not enough to match this scenario, then 2 kilograms moving 3 meters will not be. So I'm not going to bother with the calculation, which means A is a scenario where the greatest amount of energy is transferred, and because all of them have the amount of energy transferred in a period of time which is similar, A has the greatest power. So if I look at the remaining questions, again, can't find many questions on, or rather many more questions on work done in power. So let's move on to the next paper. So next paper is May, June 2023. We're looking at variant 2.2. So if I go down, okay, so if you look at question 11, a wind turbine is 30% efficient and has an output of 2.5 megawatts of electrical power. What is the power input to the turbine? So we know that efficiency is the useful output by the total input. We know the efficiency of the wind turbine is 30%. We know that the useful output is 2.5 megawatts. So if we essentially rearrange the equation to make the input the subject, you would have the useful output divided by the efficiency. 30% is essentially 0.3. So if we divide 2.5 megawatts by 0.3, that gives us around 8.3 megawatts. Again, I've expanded it out here to show the answer in watts, but the final answer they want is in megawatts. It's around 8.3 megawatts. If you supply this wind turbine with 8.3 megawatts of kinetic energy or wind energy, you get around 2.5 megawatts back. Which two physical quantities must be used to calculate the power developed by a student running up a flight of steps? Okay, so we know that power is essentially work done and the amount of time it takes to do that work. So first one we have is force exerted and the vertical height of the step only. So this is a bit of an interesting one because the student rather, goes up the steps. So although yes, the student is gaining a certain height, and the vertical height of the steps when added together will give you the total height of the stairway, it's not directly in the direction of motion of the student, and it's not in the direction that his force will act. So that's not the right answer, but that's there to confuse you. The force exerted and the time taken only. We know that force divided by time is not power. It's work done divided by time, or it's energy transfer divided by time. Work done in the vertical heights of the steps only, that is not a quantity that we are aware of. That's work done in distance. So that really isn't going to help you. And finally, you have work done and time taken only. So we know that this is probably the easiest pick because that is just the formula for power, essentially, work done and time. So that is the right answer. Again, looking for more questions on power and work done. Now we move on to topics of waves and essentially thermal properties of matter. So the next paper we'll be looking at is May, June 2023. We'll be looking at variant 2.1. So if I try and find the question on work done and power. So that's the first question there. A child runs up a set of stairs 4 times, okay? The time taken for each run is recorded. Which time is measured when the child's useful power is greatest, right? So I've given you a number of different time options here. You don't really have any data about the amount of energy that the child gains, but and it's easy to, I suppose, get confused. But the important thing to remember here is the child is running the same set of steps each time. So the amount of energy that the child gains is going to be the same each time. So the power is going to be greatest when that energy is gained. So power is greater when either more energy is transferred or the same amount of energy is transferred in a shorter period of time, or both more energy is transferred and in a shorter period of time, right? So that is essentially the 3 scenarios that you can have. And in this scenario, then it is when the child takes the shortest amount of time to climb the stairs that the child is going to have the most useful power. So it'll be 10 seconds. So again, don't get caught out by the fact that you don't really have any information to calculate the power value, because what they want you to do is apply yourself and think that the child is running the same set of steps to the same height every time. So that is just an important consideration to have. I'm just, again, having a look if there's any more questions on this topic. And no, it looks like there's a lot of really cool, interesting questions about waves and light or optics, and we'll obviously be visiting those topics as well very soon. So let's move on to the next paper for now. So we have Feb, March 2023. We're going to look at variant 2.2. Apologies, but there's been a bit of a cold doing the rounds in my house here in the UK. So it appears I must have caught the cold from someone. So I know I've been coughing the last few videos, but yeah, don't mind me. So the first question of interest is question 11. A machine has a power input of 200 watts, okay, and a useful power output of 1 kilojoules in 6 minutes. What is the efficiency of the machine? So we know that the efficiency is the useful output energy divided by the input energy. Yep. Or in this case, we have an input power and we have a useful output in terms of energy, but we also know the amount of time that the energy is transferred across. So we don't have the amount of time the power input acts over, so we wouldn't be able to get an energy value there. So the best thing to do is to convert the output energy into output power. So the student essentially, or not the student, sorry, because the last question that we saw was about a student. Yeah, just said that. So essentially here, the washing machine, it's transferring 1 kilojoules of energy in 6 minutes. So if you want to calculate the output power, it's energy transferred per unit of time. We have to convert the 6 minutes into seconds. So each minute has 60 seconds, which is what we've done here. 1,000 divided by 6 times 60 gives me 2.77 watts. And essentially the efficiency is going to be 2.77 watts, which is the useful output energy, divided by 200 watts, which is the total input energy, giving an efficiency of 1.4%, which is really low if you think about it. You're putting in so much energy, you're giving the washing machine so much electrical power, but it's only giving you that much of useful output, which isn't the best. And you'll find that a lot of instruments actually don't have very great efficiencies. So yeah. So what is the unit of power? That's the next question. That's an easy win, right? So unit of power is not the joule. That's the unit of energy. It's not the Newton. That's the unit of force. It's not the volt. That's the unit of voltage, which we will visit when we look at electricity. It's the watt. So that is an easy question. So again, have you got any more questions there? No, we haven't. Okay. So again, the reason I picked this question is you have to be able to comfortably calculate between work done or energy transferred and power, and that's what we have to do here. So the last paper we're going to be looking at is February-March 2021. We're going to be looking at variant 2.2. So if I look for the question on work done, so a horizontal force pulls a box along a horizontal surface. The box gains 30 joules of kinetic energy and 10 joules of thermal energy is produced by the friction between the box and the surface. How much work is done by the force? So you have to understand that the force isn't just moving the box, it's doing that. That's the main sort of output that you want. That's the main result of applying the force on the box that you want. But because of friction, there will always be some amount of energy that is wasted, which is why we talk about the concept of efficiency. So you could have heat. Heat is the most common source of waste. You could have sound. Sometimes you don't need the sound, so it could be it's a source of waste as well. But ultimately, the force still needs to provide enough energy to move the box and also to overcome the energy lost due to friction. So total energy transferred would be 30 joules plus 10 joules, which will be 40 joules. So that's the total amount of work the force has to do. Excuse me. The next question we're looking at is question 11. A crane is used to lift loads vertically. The output power of the crane to lift a car is P. The crane then lifts a lorry, which is 3 times the weight of the car, okay, through 0.25 of the distance in 0.5 of the time. What is the output power of the crane now? So this is a very, very good question. Yeah, because here you aren't given the mass of the car, the weight of the car. You're not given the distance it's moved. You're not actually even given a power value. You just basically just told that a car is lifted. It's lifted a certain height. It weighs a certain amount, and it's done. It's lifted in a certain amount of time. So the power to lift the car provided by the crane is P. So now you want to lift a lorry, which is 3 times the weight of the car, which has to be lifted a quarter of the distance the car is lifted and half the time. So the best way to do these types of questions, I find, is actually write out a formula for the initial scenario. So for the car, if you assume that its weight is W, and essentially it moves a distance D, and that the crane lifts it up that distance D in a time T, then the power is going to be the work done divided by the time. So the work done here is essentially the weight multiplied by the distance. Why is that? Because essentially we're transferring gravitational potential energy to the car. We know that gravitational potential energy is mgh. We know that mg is essentially the weight of the car, and h is the distance that it's moved. So if you assume that the distance moved is d, then we would have w times d, where w is the weight, d is the distance moved, and it's done in a period of time t. Yeah. So all of the variables here, I think the key thing to note as well is all of the variables here. It's not 2w or half a t or 0.25d. We're not doing any of that stuff. We are just writing out a formula for power when the car is lifted using just plain variables. So we assume the weight of the car is w. We assume that it's moved a distance d. We don't know what the distance is. We don't know the exact weight is, and we don't know what the time is. But we're going to assume we're just essentially writing out a formula. If someone asks you to write out the equation for power using just variables, you just write that out. So I always prefer to do that when given these types of questions. Start off with the initial situation, which is what I've done there. And the next thing that I've done is for the lorry, we know that the lorry is 3 times as heavy. So if the weight of the car is W, then the weight of the lorry has to be 3W. We know that the car was moved a distance D. We know that the lorry was moved a distance of 0.25D. So it's a quarter of the distance essentially. And we know that the time taken to lift the car was T. And we know that the lorry was lifted in half the time. So essentially the time taken to lift the lorry is 0.5t. So if I wrote that out, now if I wanted to calculate the power that the crane is exerting on the lorry in this instance, it's again going to be work done divided by time. We know that the work done is mgh. Mg is essentially w, h is the distance d. So we know that w is now 3 times w. We know that d is 0.25 times d. So that is going to be the numerator divided by 0.5t, because we know that t was the amount of time it would take to lift the car. So essentially, that gives us this equation here. And if we were to simplify the constants out, we get a value of 1.5. And then essentially the purpose of doing the simplification is to bring this term back into the expression or the equation. So there we have w times d divided by t. Here as well we have w times d divided by t. And we know that that is the power of p, because we were told that the power of p is w times d by t, which we've just shown using that initial equation. And here we've done the same thing. So w times d by t is essentially power. And then when we take the constants out, so we do 3 times 0.25 divided by 0.5. So we know that 0.25 divided by 0.5 is a half. And then a half multiplied by 3 is 1.5. So taking the constants out, we essentially have 1.5 multiplied by w into d divided by t. And we know that w into d divided by t is essentially p. So what we have is 1.5 times the power. So the crane is exerting 1.5 times the power to lift the lorry that weighs 3 times as much as the car through a quarter of the distance that the car was lifted in half the time. So again, 1.5 can also be expressed as 3 by 2. So B is the right answer there. So hopefully, again, these types of questions, I haven't seen them in a lot of recent papers. And by recent, I mean very recent. This is quite a recent paper as well as 2021. But I haven't seen these questions or these types of questions in 2022 and 2023. But it's good to know how to solve such a question if it comes up, because I think it's a really good question. It's just one to be wary of. So I hope you found this video useful. If you did, please like and subscribe. If you know anyone who will benefit from watching this video as well, please share the video with them. Thank you for your time. I will catch you in my next video. Bye-bye.